essentially all my research was on the effect of ceramic frit on the load resistance of rectangular glass lights. All of them are heat treated just due to the process of it. So I'm going to do a little bit of background first on essentially how the glass is made and processed and what implication that has on the strength. So as a precursor to the research, what was being seen is my professor and another colleague of mine were seeing that there was some glass Frit and Spandrel applications that were fracturing due to thermal stress. There were a couple of different projects where they were seeing that there was thermal stress breakage. It was always in the Spandrel light. And, you know, after you see so many of these similar fractures, you start thinking, okay, there must be a root cause or a similar mechanical flaw somewhere in there. And so digging a little more into the research, you see that the European codes actually currently reduce the strength of heat treated glass once you go through and apply a Frit. And there are some differences between European codes and US codes that make us being able to do this a little more difficult. But essentially what happens is in European codes, they're designing their glass using a maximum stress method. So they assume that the glass always fractures at wherever the maximum stress in the glass is. Once you go through and you apply Frit, they add, I believe it's a 30% reduction to the strength of glass. In North America, we design using ASTM E1300 generally. There are some things that fall outside of the scope of that standard, but for the most part, glass and facades is for wind load resistance at least is designed with E1300. And at this moment in time, there isn't anything in the standard that accounts for a load resistance reduction when Frit's present, even though we know that there is some impact on the load resistance from this Frit. And one of the main differences between the two standards is that in the US, we design using a probability of failure method. So it's acknowledging that there are inherently critical flaws on the surface of the glass that can cause it to fail below the location of, or below whatever the maximum principal stress in the glass is at the time. Once the glass comes off the line and starts being processed and washed and things, you start gathering these little flaws called Griffith flaws on the surface of the glass, and they become locations for concentrated stress, essentially. So in order to help prevent the potential to under design or over design, we essentially go through and we just design using a failure prediction model. So everything I present in here, I'm going to focus really on that designing to the probability of failure of 8 in 1,000. And you'll kind of see where I'm going from there. But really, where the conversation has gone is we've said that, okay, well, all of the fractures that are occurring are due to thermal stress that we've seen, not wind load. So maybe we shouldn't put it in our wind load standard or in our standard to design wind loads, right? But there is also not currently an ASTM standard in place to design for thermal stress in glass design. And so that kind of leaves this gap of, well, we know it's happening, but it's not affecting this one standard. And we don't really have a place to tell people otherwise. So we'll just kind of wait until we have something. And that's really what caused the article that you saw and you discussed in that last podcast episode, right? So if you'll move forward, okay. So just a little background in how this works. Essentially, we have our float process to create the glass. So we have our raw materials go into a melting furnace at 1500 C. Essentially, all the bubbles are pulled out. This molten glass gets poured onto a molten tin bath and is floated over that to give it the flat properties that you see. And it is pulled to be at the whatever thickness the glass is being designed to be. Afterwards, it comes out of the tin bath, goes into the annealing furnace to help relieve any residual stress that may in the surface may be within the glass, and then it is cut and packed. So that's just a general layout of how glass is made. Where this comes into play is in the next slide, where we see how frit is applied. So after the glass is cut and packaged, it's sent to a fabricator. At the fabricator's location, they apply a frit. So they could apply it through a couple different methods: roller coating, screen printing, digital print. Kate probably knows there's others that I maybe didn't mention, but generally the frit is applied onto the surface of the glass. And the frit has these glass particles or ceramic glass particles in it that after it's applied, you put it into your tempering furnace, and it's heated to a near melting temperature, not quite melting, but enough that whenever it's rapidly cooled, the ceramic frit is now fused onto the surface of the glass. So they're now one cohesive element, and it can't be scratched off. So what this does is, and this is something that whether it's fritted or not, when it goes through the tempering oven, you essentially are creating this residual compressive surface stress in the glass, and that's what determines whether it's heat strengthened or fully tempered. In this top picture, you'll see this is a piece of glass that doesn't have any frit or enamel on it, and you have this symmetric residual stress within the glass, where you have tension in the center and you have this layer of compression along the surface, and that's really what's giving it the additional strength that you're looking for. So whenever you go through and you add that ceramic frit, you see within the glass you actually have an asymmetric surface stress at the glass surface, at least, because theoretically your maximum residual compressive surface stress should be occurring on the surface of the enamel. And so when you go through, you design heat strengthened, theoretically has a load resistance of 2 times annealed glass, and fully tempered should have a load resistance 4 times annealed glass. So this is just a general background on where we're starting. If you move forward, Kate. So what I've done is I've kind of broken out, I've just taken 2 phases of what my research was to give an idea of what this load resistance reduction looks like. So initially we did some small sample 4-point bend tests, and we use this just as an observation of, does ceramic frit impact load resistance? Does it matter which surface it's on? How much? Kind of just as a gauge of, is there an actual change in mechanical failure whenever you apply ceramic frit? And then the second are uniform pressure tests, more what you would see in terms of 4-side simply supported piece of glass. And in this, we went through and checked varying percentage coverage, and we're able to see where the location of failure was with regard to the frit coverage on the glass. So we'll go over both of those. Next slide. So we'll just start with the 4-point bend test. In these, they were really small samples, nothing, about yay big, handheld. But we did 4-point bend test. So essentially your maximum stress would be the entire area between your top 2 loading pins. So that way we knew it was always fracturing at a location of maximum stress. So we went through, we tested heat strengthened and fully tempered lights. In these, we had our uncoated controls, and we tested with the frit in tension and the frit in compression to see if there was any difference with regards to where the location of the frit was. So next slide. Yeah, so here we see our just a general layout of our load at failure, or our 3-second equivalent failure load, and our probability of breakage. So we're going to focus down towards the bottom, but as looking at a general rule, you see that your control and your when Frit is in compression have fairly similar failure distributions, at least in terms of the coefficient of variance. You see a similar trend, and sorry, I forgot what I was saying. You see a similar trend, but once the Frit was in tension, suddenly the coefficient of variance significantly reduced. Now you're seeing, okay, well, whatever is breaking this, it's the same mechanical sense of mechanical failure every time. It's happening very sudden. It's happening at around the same stress or the same load every time. And so if you look at your, we'll say like mean failure load, what we started seeing was that fully tempered glass is actually performing less than at a load resistance less than that of heat strengthened, and heat strengthened was performing less than our annealed samples that we ended up testing later on. And so it's pretty significant whenever it comes to designing for load resistance. So if we move forward to the next slide, you'll see focus down at a 8 and 1,000. And yeah, I mean, it's a lot closer in this whenever you get down to probably a failure of 8 and 1,000, but we're still seeing a 40% decrease in heat strengthened glass and a 20% decrease at heat strengthened glass once you start putting that fritted side in tension. And some of the tests that we did in this, actually, we saw that the glass was fracturing at a stress lower than the recorded residual stress that we measured, which means that potentially the residual compressive stress on the fritted side isn't as high as it would be on the unfritted side. So if you, next slide. This is just a quick layout of what those percent reductions look like. We can move forward. Yeah, so whenever we realized that the glass was fracturing at stresses lower than the measured RCSS, we did use a wet etch process to remove the frit and try to measure what those residual compressive surface stresses were, and we found them to be significantly lower than that that are actually defined as heat strengthened or fully tempered by ASTM. So next slide. So now I'm just going to move forward to our uniform pressure tests. These are, you could go ahead and move forward. These are just a 4-side simply supported tests. Essentially what we did was we had these large scale tests. We put them in this frame and used a vacuum to create a uniform pressure on the surface of the glass. In this case, we were testing everything with a frit intention because we knew that was where, that was essentially where the issue was. And so, next slide. What we did was we tested our control, and then we had a varying percent coverages with this frit, and it was all a gray frit. So we did a 40, 50, 60% coverage, and then a full coverage. Move forward, and you can see here's what the example of the patterns look like. So we had our dots, our lines, and essentially the reverse of the dots. So we just had these holes. So again, here's just another, you see the distribution of them. Once we applied the frit onto the glass, all of those, essentially not sample one, everything else had frit on it. The coefficient of variation significantly reduced, so we know it's the same, probably the same reason for mechanical failure that we're seeing in our previous tests. And again, at this mean level, there's not really a clear correlation with regard to what your percent coverage is. So it wasn't like 40% reduced it this amount, 50% reduced it a little more, 60% a little bit more. It wasn't, there was no clear answer on that or solution to show how that worked. But what we saw was there was significant load resistance reduction in general. So next slide. And here's just at probability of failure of 8 in 1,000. So you can see what that looks like with regard to E1300 design. So Yeah, so what we saw was, I mean, we have essentially a percent reduction, a load resistance reduction ranging anywhere from 16 to 38%. Interesting that note on sample 2 and 4, they're fairly close in what their percent reduction was, and really their patterns were exactly just the inverse of each other, right? So it may have something to do with like the layout of the pattern versus the stripes that you know, followed a different layout. So I don't really have an answer for that necessarily, but essentially what we're seeing is that you're still getting fairly significant reduction. So next slide. Really, like, what does that mean? Well, really, when we're designing, I think the last thing as engineers any of us want is to go through and make an uninformed decision on some of this design, right? And a lot of firms are actually going through, and at least until E1300 adopts something, just either using some sort of percent reduction or just automatically fully tempering anything that has frit on it, so they at least get heat strength and load resistance. But the next slide has a little more design implications on it. Oh, I forgot about this. Yeah, so one of the other interesting things we saw really is that the fracture origins always occurred under the location of frit in all of the samples that we saw, whether it be the dots, the stripes, or the holes. You could see here on the left picture, the fracture origin occurs right in the middle of that circle of that dot. And in this, where that red arrow is, what you see is there's actually ceramic frit that is embedded within the fracture origin of the glass, which kind of leads to believe that it's potentially the frit being embedded into flaws that may be on the surface of the glass, and causing some tension on there that's essentially reducing that, what is supposed to be the compressive surface stress that's built in from your tempering process. In the next slide, there's another picture that's a little clearer. In this right picture, you can very clearly see where the frit is and where that location of fracture was. So it's always directly underneath an area where there was frit on it. And I'm on my last slide now. So, oh, I'm not. So really, some of the possible causes is there's potentially flaws on the glass surface during application. So that's why we're finding the frit in the fracture origins. And another thing may be that you're getting more heat loss on the enamel side during the tempering process. So potentially by adjusting the tempering process, you can go through and create a lower or create a more even residual compressive surface stress, but that's a lot more work needs to be done on that in order to see if that's even possible or a plausible thing to do. So really, next slide, Kate. Where this impacts design and leads into some of the discussions that you had on your podcast previously is a lot of the breaks are happening due to thermal stress. And so what things have an impact on thermal stress resistance? Well, one of the recommendations that I'm not sure who was, someone on the team said was, okay, well then I'll just design with a thicker light. If you're getting this load reduction, you could design with a thicker piece of glass, give it a little more strength. But whenever you're designing to resist thermal stress, increasing the thickness of the glass doesn't improve that stress resistance. Really, what's increasing the thermal stress resistance is your residual compressive surface stress that occurs from the tempering process. So if you are designing with frit and you have something that's heat strengthened spec, probably want to move forward and just make that a fully tempered light. Impact when you're designing for wind load. Well, by adding a percent reduction, it doesn't necessarily mean that you're going to increase the thickness of the glass. A lot of times you could add a 20%, 30% strength reduction, and it's not going to change what thickness you're selecting, because most of the time when you're designing for wind load, the glass selection tends to be governed by deflection and not by load resistance. So most of the time you won't even see a change in it with regard to your wind load resistance. Where you might see some of this change is now you're seeing an introduction of first surface bird-friendly solutions. Legislation is introducing a lot of bird-friendly glass, and so as you start seeing maybe more first surface ceramic frits come to light, that's when you might want to start taking this load reduction into consideration for wind load resistance. And so my final note that I would say is, if you're using ceramic frit enamels, I would highly recommend just fully tempering the glass to prevent breakage. I know that leads to other associated risks, but otherwise you're really leaving yourself open to potential thermal fracture risk. So now that was kind of the end of my test results, so I'll hand it over to Kate, and she could go over.
Great, thanks, Kayla. So I will present about a coating option that does not weaken glass, and then we can get to a discussion and a Q&A over everything that was presented today. So thanks, Kayla, for sharing your expertise and research on ceramic frit's weakening effect on glass. And the role that my company, ICD, played in this research is we actually participated in a white paper that was released probably about 5 years ago now, alongside Texas Tech University, Chris Perry, glass consultant, Dow, and a facade engineering firm called Morrison Hirschfield, to determine whether silicone coatings, which is an alternative to frit that is applied after the heat treatment of glass, also has the same weakening effect. So I'll be showing you the 4-point bending test results of silicone, as well as ball drop testing, which is not related to thermal stress, but it also gives a hard number on the impact resistance of glass. So I always like to start with just a brief definition of what spandrel glass is, because in the podcast, I know maybe there was some questioning about why it's used. And so first, I like to just show that spandrel glass should always be near opaque, used in non-vision areas, interior surfaces not suitable as a finished wall, and it must be cavity backed. So if it doesn't have a uniform backing in place that completely eliminates light transmission, otherwise you're going to see application textures, pinholes, and just general non-uniformity as seen in these photos. So once installed correctly, it will appear 100% opaque. It can be used for its functionality, so it's commonly designed to conceal structural and mechanical elements from exterior view, such as floor slabs, vents, electrical wiring, mechanical systems. And from a design perspective, it can be used for aesthetics, so decorative applications to have, bright, fun colors, material mimicking. Sometimes architects and designers will send in physical samples of, for example, the framing that's going to be used around the glazing, so the spandrel glass can match that. Retrofit or rescan applications, or to have a contrast on the facade. Or harmonizing, which is one of the more common design goals, is where you want the entire facade to have that nice seamless blended look, and spandrel glass can achieve that as well. So now I'll just show some examples of how thermal stress breakage occurs in spandrel glass applications. So thermal stress occurs because of solar gain, even though there are reflective and low-E coatings that are sometimes used for the spandrel cavity, often used for that visual continuity. Solar heat energy can still get through between the glass and the spandrel insulation, which heats that cavity up. Then the center of glass heat loss is somewhat restricted. So if you do have a reflective or low-E coating, along with the composition of an insulated glass unit, it reduces heat loss to the exterior. And then the insulation, the cavity backing behind the spandrel glass, reduces the possibility of heat loss to the interior. So therefore, that cavity gets very hot. The solar gain, coupled with the restricted heat loss, allows the center of glass portion of the spandrel glazing to become very warm. And at the same time, the surrounding framework chills the perimeter of the glazing, so the warmer center of glass area expands relative to the colder perimeter, creating tensile stress. And it's when the stress exceeds the strength of the glass when breakage can occur. So here is a visual of the center of glass area, which gets hot from solar gain, surrounded by a perimeter area that is cooled by heat loss through the framing, which can result in a crack forming. Now, annealed glass, which is just referring to glass that has not been through the heat treatment process, takes a temperature differential of about 91 degrees Fahrenheit to induce enough tensile stress to cause breakage. So when you see a single crack like here on the left, the temperature is likely within that range. But when the cracks begin to branch out like this, that tells us that the temperature difference might be much higher with more stress in the glass, with heat-treated glass. So here's just a real life example of a building that had glass that was broken due to thermal stress. So there was an insulated glass unit that was heat treated for the spandrel with a low solar gain low E coating on surface number 2 and an insulated sheet metal backpan behind the glazing unit. And the inboard pane of glass is cracked with a ceramic Frit opacifier applied to surface number 4. And looking closer, we can see the top of that crack and how it branches out at the spacer with temporary support installed to hold the glass in place. And zooming in, you can see the fan, and the branching of the crack is actually starting out above the spacer. So not right at the edge, but within the depth of the spacer and perimeter sealants. So taking that unit out and flipping it around, now we are looking at surface number 4, which is referring to the interior facing surface with an applied ceramic Frit. The crack is on top and moves downward toward where it fans out to the center of glass area, and the crack progresses toward the edge of the glass, fanning outward in that direction as well. And this tells us that the crack origin is somewhere in this region between the two fans, which is significant because cracks in annealed glass typically begin right at the edge of the glass. And in this case, the crack is clearly beginning inward away from the edge. So basically what I'm doing here is just showing visual characteristics of glass that has been broken due to thermal stress. So now we're looking at the face of the crack on one half, and there are components that tell us this is the origin. First, there's a semicircular shape referred to as the mirror. Outside of the mirror, there's a fine pebbled area known as mist, and following that's a jagged radiating pattern known as hackle. So collectively, this tells us that the crack began up at the top on surface 4 where the Frit is applied and radiated downward to the left and to the right. And at the bottom, we see a wide black band. This is the perimeter sealant and spacer, showing that the geometric center of the mirror is within the depth of the spacer, not at the edge, but inboard from the edge. So naturally, one of the questions that arises when discussing thermal stress is how can I find solutions on how to prevent breakage occurrence, right? And so a common question that arises is, can ventilation be used to remove heat from the spandrel cavity? And with rain screen wall design for brick, the cavity is typically drained from behind the brick to the exterior to remove moisture that may penetrate. And vent holes are included at the top of the brick panels to provide opportunity for air to flow through the cavity and help dry out that moisture. So Morris and Hirsch Field Engineering firm carried out a test program to determine the effects of ventilating spandrel. So here is a simple test assembly. There's 2 frames of 3 panels. The 3 on the left are just monolithic single pane, and the 3 on the right are insulated. And here the glass is clear, so you can see the insulation and wiring that was used to calculate temperatures from within the assembly, and that will also be used as a control against the opacified unit results. So the first approach is to fully seal the perimeter of the glass, typically occurring in a 4-sided structurally glazed application. The second condition has only drain openings at the bottom, which is the traditional approach for draining spandrel. All spandrel glass applications should have some sort of water mitigation system in place to eliminate moisture buildup. And the third has vent holes at the top and drain holes in the bottom to test if you can get the same air circulation benefits that are known to occur in brick masonry, and see if this method can remove heat that can build up in the cavity. So now analyzing the results of that testing, first we're looking at the graphs of the 3 conditions with clear glazing. The orange line is the sealed 4SSG, the blue line is the drained, and the green is the vented. And with monolithic glass, venting seems to have somewhat of a small beneficial effect, but all 3 are well below that danger zone of, this is in Celsius, so 35 degrees Celsius, where thermal stress breakage could happen. So spandrel ventilation does not make a difference. And with insulated units, there's not much of a difference between the three options, and we're just starting to reach the level of danger of thermal stress breakage. Now comparing against the opacified results, looking at the condition for monolithic, the temperatures increase but are still below that 35-degree critical range. But for IGU, you can see they now start to reach out of that range. So there's a risk that can be dealt with by heat strengthening the glass, but adding a ceramic frit can take away some of that benefit, as we saw in Kayla's presentation, and I'll be showing a coating alternative in the next few slides. So both silicone and ceramic frit have been through environmental durability testing to prove that they can withstand long periods, very long periods, decades of exposure to weathering, such as UV, very hot and cold temperatures, and varying levels of humidity. So just to briefly introduce silicone coatings as an option, I'll define them for you. So silicone is a water-based formulation, and that is one of the advantages of using silicone, is that it is a sustainable, eco-friendly alternative to frit, which can be really helpful when architects are designing for LEED projects or other green rating systems. So silicone and glass actually have a very similar chemistry makeup. The primary constituent of both is sand. And so there's a very strong natural bond to one another, and the attraction is very high. Silicone's cured through the evaporation of water ambient or very low temperatures, and after curing, it becomes a durable, tack-free, elastomeric, rubber-like film with outstanding adhesion. This table addresses some key differences between these two specified spandrel glass products. As we saw, frits applied before the heat treatment of glass and then fused. Silicone coatings are applied after that heat treatment process and then cured at ambient or low temperatures. The coating composition of frit can cause glass to weaken, and the natural bond of silicone does not weaken glass. So we saw that studies have shown that frit can weaken the tensile strength of heat-treated glass by about 40 to 50%. Tempered glass can be used to mitigate that risk. As Kayla mentioned, there are some other risks associated with tempered glass. It is very rare, but it does happen. Essentially, there's a risk of spontaneous breakage due to nickel sulfide. So when glass goes through the tempering process, nickel sulfide stones can form due to contamination and end up in the center tension zone of the glass. And later, when that glass is exposed to varying temperatures, that tiny stone can grow and cause the glass to shatter spontaneously. And so to expose these nickel sulfide inclusions, glass can be heat soaked in very hot temperatures. And I'm seeing a lot of glass fabricators add heat soaking capabilities to their line. And even on an international scale, a lot of projects in Europe and Asia are just heat soaking all the glass in their projects. But this is a very expensive and timely process. And even glass manufacturers do not always consider it 100% effective. So just to quickly go back and recap, overall frit's weakening effects, breakage can occur in monolithic glass, insulated glass at a higher risk, silk screen patterns, and full coverage, which can also have a higher risk. Silicone coatings do not weaken heat-treated glass whatsoever, which can therefore reduce risk in breakage. So I'll show the results of the silicone-coated glass for the 4-point bending test. First, we're just looking at the results for heat strengthened glass. And again, we have a similar testing arrangement. And this was also tested to that same ASTM standard that frit was tested. And we have the probability of breakage on the vertical scale against the equivalent stress on the horizontal scale. And you hit 100% probability for the clear, which is represented by the blue line at around 600 600 pounds per square inch. And the orange-red curve shows us the probability of breakage for heat-strengthened glass with a silicone. Loads are slightly higher than uncoated glass, therefore significantly higher than what we saw of Frit. And then we have the tempered glass samples, and with uncoated, you hit 100% at around 680, while the orange-red line shows that silicone holds a similar load, but there's no weakening effect and still is higher than that of ceramic Frit. The conclusion is that there's no tensile strength loss in heat-treated glass coated with silicone. And I just wanted to point out a unique characteristic of silicone, which has an elastomeric nature. So it gives it the ability to naturally achieve fallout resistance when applied at a certain thickness. So fallout resistance refers to 6 millimeter tempered glass that, if shattered, can be temporarily retained into the building until it can be replaced by the owner. And if you apply silicone at 13 mils wet film thickness, it automatically qualifies for that fallout protection, while ceramic Frit needs an applied film, which can add cost, added material, added labor. So this is a cost-saving strategy. This is not a substitute for security or safety glazing. It's its own category, but it could offer an added safety factor to prevent broken or shattered glass from falling from the cavity. So I'm just going to quickly show this ball drop testing because it was tested to determine the fallout resistant effects and impact resistance. So it just used a simple box frame to support the glass. The coated surface is on the underside and in tension when a weighted ball is dropped onto these samples of glass. Then the maximum height achieved before breakage is recorded. So I'm actually going to show a fun video that demonstrates the results of this testing. So first, clear uncoated tempered glass was tested with increased height, and breakage occurs at about 4 feet. Next, the test was repeated on tempered glass with the silicone coating alternative to Frit applied after the glass tempering process. And you can see the silicone coated glass achieved much greater heights. I believe in this testing it went up to about 11.5 feet. And now we have the results for ceramic fritted glass. And the glass breaks at a very low height. So the ball drop experiments in this video support the fact that silicone coatings do not weaken the impact resistance of fully tempered glass while ceramic Frit can. So here's just a comparison of these results in graph form. And on the right, we're looking at the conditions of just the two coatings and comparing changes in terms of percentage. There's a 51% increase with silicone and decrease of 69% for a Frit. So the recommendation that we have is a hybrid approach of acknowledgement that Frit weakens the glass. It's not a well-known fact in the industry. I mean, there's been a lot of studies, but in terms of architects knowing about this, glazers, it's not always known, but it is starting to be talked about more, especially as it begins to potentially be incorporated into today's standards in North America. So if it is used in the design, just being able to account for it in some way, or just from an awareness perspective, so that it's always good to have all the information. You can also change the opacifier to silicone to avoid this load reduction completely and design at full load capacity. But you should always review design capabilities with the coating manufacturer. Silicone coatings cannot be screen printed like a ceramic Frit. It's only for the full flood coat applications for Spandrel. So specifying for performance, specifiers can note that silicone does not lower the tensile strength of heat-treated glass, and if a substitute Spandrel coating is selected, it's important to understand its effect on the tensile strength of heat-treated glass. So I always just like to point out this reminder because there still are misconceptions out there that silicone is a Frit. So just like to remind that it's a completely different coating technology. Both Frit and silicone are great choices for use on facades and are very trusted and perform well, but they do have their differences. And the one that was discussed today was about weakening effects. And that 69% is actually referring to the including the impact resistance of glass. As we saw earlier, the tensile strength reduction is about 40 to 50%. All right, and that's just a quick recap of everything that we covered today. And that concludes my portion of the presentation. So I want to give a big thank you for allowing us to be here and present to your office today and partake in your podcast. Here's my information and Kayla's information. And now we'll take any questions or comments.
I have a couple questions. Is there a huge cost difference between ceramic, Frit, and the silicone?
That's a good question. So there's a two-part answer to this question. From my perspective, we only manufacture the liquid coating, which is a small component of the entire glazing system. And the fabricator who's applying the coating to glass, who's heat treating the glass and constructing it into IGUs, they're setting that final price of the coated glass and selling it to the glazer. So it can be on a project specific basis, but from a general sense, they tend to be very competitive in terms of cost. And I would say that the most important thing is working with a fabricator that is certified to supply silicone, because they do have to go through a training process. And if the fabricator that's awarded the job does not supply silicone, they might tack on an extra charge to have to source it from somewhere else. So that's why I always recommend having the contractor get in touch with the coating supplier and get a list of those local fabricators.
What light is the silicone applied to? The inboard light, the outboard light, what surface, I guess?
Yeah, it can be applied to essentially any surface except for the exterior facing surface number 1. It has to be completely masked and protected. So there are considerations with IGUs. It's most common on surface number 4, because if it's inside that airspace, it has to be edge deleted or cut back around the perimeter to allow for the sealant to adhere to the glass. And if there's a low E coating in the IGU, there's also compatibility issues with the silicone. So most commonly it's surface number 4, or by default 2 if it's monolithic.
And then my final question is for Kayla. If there is issues with the surface of a glass not being perfect, having imperfections, which we all know is true, has there been any research into applying a laminated coat on the surface before the Frit is applied, so that the Frit is adhering to the laminate and not directly to the glass itself? Kind of like what we would see in an insulated glass unit that has been impact rated for hurricanes. The inboard light is actually a laminated, IGU essentially.
Yeah. So part of the issue is that to reach the temperatures that you would need to fuse the Frit onto the surface of the glass, you're getting it to near molten state, right? So a lot of times these laminates won't survive temperatures that high. It is possible to go through and get opaque laminates and laminate your inboard light. That's absolutely a thing you can do, but then it's still the risk of like building up that thermal stress within those lights. So you would still need to heat strengthen those as well, either way. And once you start introducing laminates, then your price starts increasing even more, because now you're taking on the cost of 2 pieces of glass plus that specialty inner layer. And so, yeah, you can't necessarily laminate the Frit onto the surface, but you can use opaque inner layers if it's an option that you wanted to go through. It's just more expensive.
Got a question. Thanks for sharing this with us. And have you heard any new? I know the industry is kind of pushing to implement photovoltaic cells into some of the IGU units and laminate units, and that's kind of still in the early stages, But when you mentioned that thermal change in these units are culprits of breakage many times, heat gain increase and all that, has there been any more research about the addition of the photovoltaic cells to act as like solar panels in IGUs, and what is the impact of that on like breakage? Have you had any experience on that? Yes.
Yeah.
To either Kayla or Kate.
I'll let Kayla take that one.
Yeah. So with regard to building integrated photovoltaics, now we're starting to see the introduction of transparent PV, where you don't have the opaque back painted Frit, right? It's essentially just your standard window that is using a coating to collect some of the solar energy, right? And so you don't run into that because you're getting similar performance to a standard window with regards to your heat buildup, your U factor, your solar heat gain, things like that, but you're just essentially collecting the sun's energy and then storing it in a battery or putting it back into the grid, or whatever magic happens at that end, right? So with the introduction of like transparent PV, you don't have that issue. With regard to standard PV, that, whether it's rooftop or whether it's something that would be installed, in a Spandrel application or in those opaque spaces, most of the time, honestly, those are already fully tempered. Because, if you think about a lot of the rooftop applications, and it's dependent on where it is, but it's already having to undergo a lot of this like significant weathering, potential like hail impact, going through a lot of this testing already. And so most of the time those are already fully tempered, and that's why you don't have the issue there. It's just more whenever you start getting into your actual, glazing designs, a lot of times, because your Spandrel application, it's usually smaller lights. And so since it's smaller, they're not fully tempered because you don't need that additional, or you don't think you need the additional resistance since you're using lower aspect ratios or something along those lines. And so that's really where the I guess miscommunication is on that part. But with regards to BIPV, it's either already happening or it doesn't need to, because it'll be transparent.
Yeah. Okay. Cool. Thank you.
Yeah.
I have a question. My name is Matt. I'm curious. You guys mentioned the difference between European and U.S. standards. We deal with this a lot, with the U.S. standards being a little bit behind European standards. Do you guys know of any push to get your studies put into the U.S. standards? Because that's one thing that we struggle with quite a bit is when we know something exists, as engineers we have to do our due diligence. However, we're swimming upstream trying to change an industry. And it becomes really challenging. So just curious to see if you guys are pushing towards that at all, or.
Yeah, so with regard to the glass industry, I think everyone, like, I'm on a lot of the different ASTM committees for these glass design standards, and I think we all acknowledge that there is we're playing some catch up, right? But part of it is that not as much money is funded into the research in the US on a lot of this. So we are also learning and then trying to incorporate and develop. But yeah, there is movement towards including this into the standards. Usually the way it works is we have a standard and then it goes through essentially like we publish it and then it goes through like a 5-year review process. So once we publish, we're already starting all over again. And all right, what's next on the wish list? What's next on the wish list? And so we have this running list of things that we're trying to tackle, right? But this is something that has been discussed and been on the wish list for 10 years now, essentially. But then it just comes into how do we all agree on how to incorporate it? So we should be seeing the updates within the next year or two on these in there. And I know it's still waiting another year or two, but it's where we are, right? And so, yeah, I hope that answered.
Yeah, no, that's what I was curious. Thank you.
Yeah.
Kayla and Kate, excellent. This has just been an excellent presentation, and both of you are extremely knowledgeable. And I found this to be really good. I do have a couple questions. I have a question about availability of fabricators and manufacturers to apply silicone versus ceramic frit? Do you find that there's, a discrepant or a great disparaging difference between the availability of manufacturers that will do this?
At this point, no. We have many certified fabricators all over the globe. Some of those fabricators carry both frit and silicone. Some only carry one or the other. But typically, regardless of where your project is located, there's going to be at least a few options around that can supply it. And I'd be happy to send you a list of suppliers, silicone coating suppliers near Missouri or wherever your projects that you're designing are. So.
Great, good to know. The other question I do have is it concerns compatibility in the IGU makeup. Are there any compatibility issues associated with silicone and various different spacers?
So yes, we have a list of approved materials that have gone through a compatibility testing process. The main one that should be avoided is neoprene in terms of incompatible use. But I can provide that list of materials, but it is important that glazers follow the guidelines and do not use incompatible products, because especially with coatings and coatings applied post heat treatment, you do have to think about off-gassing and how it can react in the system, because it could happen within a period of months or it could be years down the road, but you could experience failure at some point if you don't use a product that's been tested. So but we do have very extensive lists of materials that we recommend, so I could send that your way.
And then any known incompatibilities with gas fill?
To my knowledge, no. I don't believe so. I'll have to confirm that, but none that I've heard of.
Great. Awesome presentation.
Great. Thank you. We really appreciate your time.
Thank you so much for having us.
Yes. Great questions. All right.
For those of us who have PE licenses, are there any continuing education units?
So I can provide a course completion certificate if there's anything that you can self-report. This presentation is not certified with any organization, but if you're able to self-report any credits, I'm happy to send over certificates. And I will say ICD does have an on-demand course about thermal stress breakage that I can send. It's AIA. I don't know if there's anything that can transfer over from AIA for PE, but if you would like to take that, it's almost the same material, so you could just have it on and take the quiz at the end, but I can send you the link for that.
Sounds great. I'll send you a list of our PEs here. We would appreciate those, any certificate that, will
Sure.
help out. Yeah.
Absolutely. Happy to do that. All right. Well, I can also send over confirming that it's okay with Kayla, a copy of the slide deck, just a PDF file, or at least the slide with our contact information and just a few key points, if you would like to keep it on hand for future reference.
Yeah, I think that would be great.
Awesome. All right.
Similar to what I said earlier, if you would like, I'd be happy to share. There were a lot more phases than what I presented. Those are kind of just the general layout, but I'd be happy to share some of those papers and information with y'all as well if you're interested in, because we did additional testing with regard to fully tempered with heat soak, using digital printing, using other types of applications. So there's a lot more if you're interested in seeing those.
Thank you much. Well, thank you again. Really appreciate the presentation and your time this morning, and look forward to future discussions about this. This is awesome.